In this lecture, we will deal with some of the aspects of multi-scale analysis in experimental mechanics and the trends in experimental mechanics. And what we will look at is important aspect, whether you could do multi-scale analysis in experimental mechanics. This is also very important, because now miniaturization is the order of the day. People would like to make it as small as possible, and you will also like to find out whether from a stress analysis point of view these miniaturized components are stable and whether they will do the intended surveys, whether they will come for the life that you talk about. So, multi-scale analysis becomes important. Suppose you take a strain gauge technique, what happens? The physical gauge length determines the size on which I can operate. I want to do it for a single point, so I want to have the gauge length as small as possible, and for very miniature components, strain gauge itself, when you paste it, it will reinforce the specimen. So, we do not want to use, we will not be in a position to use in such applications. On the other hand, when you come to optical methods, it is the optics which dictates what is the scale in which I can operate. And once you get into this, researchers have developed specific equipments, and you have that available in the literature, and it is very important that you need to have some of these in your notes, so that you know how these are used. So, what I am going to give you is, for each of the technique, what is a key paper that will give you an idea that this is also applied at a different scale. And in order to save time, what you could do is, rather than writing the journal name completely, you can write it as an abbreviation, and also write the first author and put et al. For you to access it. So, photoelasticity at microscale, you have H. Fessler et al. It was published in 1987, and you have a micropolariscope for automatic stress analysis. This was published in Journal of Strain Analysis for Engineering Design. You just write it as JSA, and the issue number and page numbers are noted. So, you abbreviate this reference, and this also gives you an idea what are the journals that you should look at for you to get additional information on experimental mechanics. So, that information also you get indirectly from the list of references you have, and you should also know photoelasticity is applied at microscale. We have already seen Moire, we have already seen holography being applied at microscale, and these are all very important information for you to know how experimental mechanics can be applied. So, Moire analysis at microscale, you have Han and Post in 1992, and they have come out with an immersion interferometer for microscopic Moire interferometry. This has been published in Experimental Mechanics, write it as EM, that is good enough. So, what you could do is, you could just write the author, year, journal and the page reference. With this, it is possible for you to access the information in the library, and you could have a look at those papers. And N.S. Leo and V. Prakash in 2000, they have come out with a Moire microscope for finite deformation micromechanical studies, again in experimental mechanics, and you have the page numbers. So, just write the first author, year, abbreviated name of the journal and the page number. This information is sufficient for you to look for these journal papers later, and likewise we are going to do it for each of the technique, what is the available reference, some of the key references. You will have several references given in the end of the paper, that will also give you an idea what way you can go about. Then you come to holography, You have a paper by C. Brown and R. J. Pryputniewicz in 1998, published in Optical Engineering, you can put it as OE, and this was for holographic microscope for measuring displacements of vibrating micro beams using time average electro optic holography. So, micro beams, all these have become important from nano level studies now. People are going in for miniaturization. So, you have to find out whether these components are stable at those scales. And speckle methods, you have U. Paul Kumar and others, published in 2008. It is published in Optics and Lasers in Engineering, you could abbreviate it as OLEN. So, it is published in OLEN, and these are all the page reference, and this we had seen when we looked at speckle methods. We were getting the pressure sensor, it is a rectangular pressure sensor, and you have this out of plane displacement was recorded by speckle methodology, and it is a MEMS application. Then we move on to nanoscale studies have been done, and digital image correlation in conjunction with an atomic force microscope. And that is what I have been saying, digital image correlation is an emerging technique. The greatest advantage is if you are able to control the size of the speckles and also improve your optics, you could conveniently study at different scales. And here you have a paper published in 2007 by T. A. Burfield in experimental mechanics, you can put it as EM. This is on micro and nanoscale deformation measurement of surface and internal planes via digital image correlation. As I had mentioned earlier, you need the lead author, name of the journal and page reference. This should be sufficient for you to go and search for the paper. So, you have seen you have to look at experimental mechanics, optics and lasers in engineering, journal of strain analysis, and you can add to this list experimental techniques. These are all the journals that you would be finding it useful from the point of view of looking for additional and recent information. And you also have holography at nanoscale. This is essentially a group led by Pryputniewicz. They have done extensive studies on MEMS, and mind you, this is about 3,60,000 RPM. You have a micro gears rotating at 3,60,000 RPM. People have done experiments on such miniaturized and such high speed applications, and this is done by stroboscopic optoelectronic laser interferometry microscope. It is a very sophisticated methodology. Only very few people in the world could achieve such high level of precise experimentation. So, it is very interesting. I thought that you should know, it is not few thousand RPM, it is 3,60,000 RPM, very high speed rotating gears. So, here again this is in a proceedings of SPIE. So, you write that 4101B, these are all online accessible. So, write the lead author, year, and then go in for the reference. Now, the other aspect what we will have to look at is what are the trends in experimental mechanics. So, one of it, once computers are developed, numerical techniques became very popular, and if you do not use computers in experimentation, you will also fall back. So, computers are also being employed in experimentation, and what you find is they have been used extensively for data acquisition, and also has significantly changed the way in which experiments are conducted. This is a very important aspect. Earlier people have to go and wet their hands, now it is all press of a button. So, what you find here is when you have experiments on large scale structures, collecting data by strain gauge was a nightmarish experience. It is no longer so. With computer data acquisition, multi-channel strain measurement of thousands of channels is very simple now. The technology is so well developed, electronics are so well developed, because the switching and then scanning, all this need to be very carefully done when you are having thousands of channels. It is one story to have 4 channels and make measurement, it is totally another story when you have more and more channels added. The technology is different and it has to be precise. And another advantage is, it is not only you measure strain, you also need to measure temperature, you may also have to measure in a system pressure. So, what you have is, with strain gauge based temperature, pressure sensors, it is also easy to record temperature, pressure at specific locations. So, what you have is, you measure strain, you also in a position to measure temperature, you are also in a position to measure pressure, and some of these will always come in a combination. You may have to, if you are really looking at a structure how it behaves, you may have to have this data. So, now I can have one data acquisition system which could record in some points temperature, some points strain, some points pressure. So, I need to identify which are all the locations where I want to do. And what was possible? What has made this possible? Technology, electronics. And you can also measure displacement using LVDTs. They can also be combined to the multi-channel strain measurement. So, experimentalists now have more choice in planning an experiment conveniently. I have always been mentioning, experiments are planned and executed. You anticipate values. Unless you anticipate values, you will not know what instrumentation to use, and anticipation of values also helps you to look for surprises. You need to have an open mind when you do an experiment. You will have to have and take the surprises, find out why you have a surprise information. In most cases, it may be because of certain approximations you would have done in your analytical or numerical methods, which would have escaped reality. It has several times happened. Experimental measurements or truth, raw data is very, very important, but you should record raw data as accurately as possible. When I say raw data is important, you should find out how an experimental technique has to be carried out, follow all the steps and record raw data as accurately as possible. Then raw data is sacrosanct. If you take a very casual attitude in doing the experiment, raw data is no longer sacrosanct. So, if you record the raw data and you find surprises, first thing you go and find out, have you made any approximation in your analytical modeling or numerical modeling, which could be improved so that those results will match with experiment. In fact, if you take a simple cantilever and put an end load, and if the cantilever has sufficient depth, your experimental measurement will definitely be different from your PLQ by 3EI approximation, because you ignore shear deformation in that formulation. So, you can't go and say the experiment is wrong. You have not accommodated shear deformation in your formulation, and your experiment has revealed there is a slight variation. The variation will be small. If the depth of the beam is more, if shear effects are predominant, then the deviation will be more, and it again depends on the sensitivity of your measuring system. If the measurement system is accurate enough, you will be able to see the difference. So, that is how you have to look at it. And now what you have when you have a complex situation, because you have one multi-channel strain measurement can accommodate temperature, pressure and displacement sensors in one platform, it makes your life lot more convenient and help you to plan your experiment much more intelligently. Then what are all the other development that has influenced? And what you have here is, there are two aspects. Data processing is now very fast. For example, double exposure techniques, you can make it appear more as real time when you do computer processing, because your processing of computers is very fast in handling large scale images. This is not the only advantage. If you go and look at thermoelastic stress analysis, or if you look at digital image correlation, and you can post process the measured data, temperature, strain or pressure, they could be represented in a manner convenient for an user to interpret the data. This is not only for the techniques like the image correlation, even strain data when I have, suppose I have a multi-channel system, I have strain data developed at several places, I would like to see a visual representation even at point information if I get. So, the colors, if you put it in color, you are able to react better, this which you have been doing only in numerical techniques, which can also be done in experimental technique with the availability of computer processing. Then what you have, I have already said, the CCD cameras have replaced human eye in all the optical methods. So, what you find is, it has brought about a fundamental change in data acquisition in optical techniques. The advantage here is, I could record intensity information using CCD cameras at several frames per second. This has modified the experimental approach developers to find out new ways of processing this intensity information. So, what you find now is, you have techniques known as phase shifting techniques have come into place, and they are the norm for most of the optical methods, where one aims at acquiring quantitative data at every point in the model domain. This was unthinkable earlier. If they have to record intensity, they had a photomultiplier tube and it has to be moved over the model domain, and you have to process data, it is time consuming. Now, with CCD cameras, I get intensity data over the field at several frames per second. So, I could also record slowly varying time phenomena. With high speed cameras, it is also possible to record dynamic events. With appropriate optics, you could record multiple images. So, technology has really advanced with the development of computers, and experimental methods have taken full advantage of it. So, this is the positive side of it. What is the other aspect? And people want to have user friendly equipment. So, when they have goal as user friendly equipments, the systems are developed to an extent that one looks at the final result in conveniently colored plots. What is the outcome of this? The equipments are astronomically priced, with no educational institutions could afford to buy easily. That is becoming the trend. This is one aspect of it. The other aspect is, I have always been saying there is joy in looking at fringe pattern, and fringe pattern has lot of information, and you have this information, you can make certain judgment based on looking at the appearance of fringes. And with modern developments, what has happened? One does not even look at the fringe patterns that could give valuable qualitative information, and in the process the physics of fringe formation takes a back seat, which could be dangerous in critical situations. A similar thing happened in development of numerical techniques also. Once finite element got stabilized, so what they found was now we have a very good software which can do all problems. So, no engineers are required, science graduates who know how to run the computer program are sufficient, and that way the industries can bring down the cost of analysis. Then they burnt their fingers, they found that boundary conditions are very, very important. The science graduates know how to operate the program, but they do not know what to feed to the program. Then they had a scenario where you will have a team leader as a doctoral candidate with a background in engineering who would decide on boundary condition, and you will have set of people who will run the software. And a similar situation is also lurking on experimental mechanics. So, you need to have user friendly equipments, fine, but it should not go to the extent that physics of the fringe formations takes a back seat, the physics of the methodology takes a back seat, and you press only buttons. So, that is not the way the experimental mechanics should go. And the caution here is for well established techniques for specific industrial applications, particularly if you go and look at glass manufacturing, they employ photoelasticity, and when they employ photoelasticity, what they do is they have to control glass process parameters. For this, they have well developed equipment, you have to press few buttons and then keep monitoring the process. That is a specific application where you need some level of automation, some level of fast response. For such industrial applications, this kind of user friendliness may be all right, but they are not good in a learning or research environment. So, you need to find out make a difference. When I am in a research and learning environment, I want to know everything about the experimental technique, I want to know its advantages, I want to know its limitations, because in a real scenario I may invent a new methodology to extract information in the way I want it. I do not want to go and use it as a black box, press some buttons and report the results. That is not the way a learning and teaching environment should be. So, in this course we would focus more on physics behind the experimental techniques, and that will give you certain level of confidence. Although phase shifting methods are norm of the day in optical methods, we would focus on the conventional approach of looking at fringes, so that you gain insight into experimental method as well as improve your understanding of solid mechanics, because many of those things you would have just seen it in the books as equations, and when you see them as fringe patterns, you also have an appreciation how the values are at different points on the model. It will also reinforce your understanding of solid mechanics. In this lecture, we have looked at the multiscale analysis in experimental mechanics and also the trends in experimental mechanics.